Hey you, welcome to our class, and we continue with chapter 8, Pure Mathematics 1, Differentiation for A-Level, Cambridge edition, Oxford. And we'll be looking at differentiation, commonly known as the change in y over change in x. We usually can quickly remember differentiation by that. As calculus is a study of the rate of change between variables, it is also good to know that differentiation can be used in a huge number of real-world applications. So this calculus can be used in many real-world situations, and scientists use differentiation to analyze the growth of bacterial population change, the number of hours of daylight throughout the year, and this is another concept that we studied in physics under radioactivity and in chemistry under radioactive decay. So here we are going to look at radioactive decay and the inflation rate in finance, just a few of them, because generally differentiation and calculus can be applied in many places in real world situations. So this is what we are going to be looking at in terms of differentiations. Let's look at the chapter overview for this course. One of the objectives that we are going to focus on in differentiation, as far as this is concerned, is for us to be able to understand the idea of gradient of a curve at a point as the limit of the gradient of a suitable sequence of a curve. So we'll look at gradient, how we can be able to find a gradient of a curve. On that, we are going to look at tangent line, and we know that a tangent to a curve is a straight line that touches the curve only once. So we will look at the gradient of a curve, and we will be able to find the gradient of those curves. And it is good for us to know that we are going to be using some notations when we write f prime of x. As you can see here, if we write f prime of x, so this becomes So if I write f prime of x, it takes you to the first derivative after we have differentiated the word once. So what you can see here, f prime of x represents the first derivative of the function f prime of x, and we can go ahead and differentiate this 2 times. This will be the second derivative of the function, and all these represent the same thing. We can actually do dy dx, right? So we are going to be using all these notations in calculations. Of course, we will use the derivative of x for any rational number n together with constant multiple sums, differences of functions, and of that composite function. So we've talked about composite functions, a function that can be applied in another functions, and we looked at also the inverse of the functions under chapter 3 earlier on when we were dealing on functions, and we will look at how we can apply differentiation in gradient, tangent, and the equations of the normals. So this will be what we'll be looking at in this particular topic. Conceptual understanding. From Topic 7. What do we know in terms of how to rationalize a simple expressions? So we have this expression, right? Rational expression in the form of ax to the power of n. And we have some example. When you have these particular notations and we want to rationalize it, it is good for us to be able to pay attention and look at what is required for us to do. If you look at this, we have 3 divided by x squared. And we are supposed to rationalize this in terms of ax to the power of n. Ax to the power of n. What we have to do is to remove the fractions. So we simply have to take the denominator and multiply with the numerator. So we are going to have x, and when we remove this and bring it upward, it becomes x to the power of -2, because it is like trying to flip the inverse of that function. So we are going to have 3x to the power of -2, and if you take it back, it becomes 3 all over x squared. So it is just like maneuvering all this and trying to flip over it. So this is what we did here. And the second one is the same thing when you have root x. In this case, if it is root x, we know that root sign of x, so remove the side, it is simply going to be a half. So when we work on root x, we simply take, usually root can be given as a half. So root x in this case will be x raised to a half. And we can do the expression, the same model for what we have here. 4, we have 4 divided by root x. So if we change this in terms of x, that is ax to the power of n, this becomes 4x to the power of -1/2, since it is on the denominator. And this is how we do these simple expressions. So ideally, you're supposed to have done this under chapter 7, so that you are able to now apply this concept in differentiation. Now, the first thing we want to look at is the gradient of a tangent. And earlier on, I have indicated what is a tangent. A tangent to a curve is a straight line that touches the curve only once. So you can see the curve. This is a curve. A curve is not a straight line. It is a curved line. And when we draw a straight line that touches that curve at once, at one particular point, we call it a tangent. Even when you draw a circle and then the line touches the circle at one point, that is a tangent to the circle. But in this case, we have only a curve, not a circle. So the line drawn is a tangent curve. So the tangent to a curve at any point P, like you can see, point P is any point where the line touches the curve, B at the point where the line touches the circle. So the tangent to a curve point P, and by the way, you can call it any letter, it must not be P. So that point P is the straight line that touches the curve at P. Of course, we are going to look at how to find the gradient of the curve at any point, and we are simply going to use the formula that we know, change in y over change in x. We have already talked about how to find the change in y over change in y over change in x can be given as the difference in those two numbers. So we take y2 minus y1, divide this by x2, and again you can as well do y1 minus y2, divide this by minus x2. The only thing you have to be careful is if you start with y2, you must start with x2. If you start with y1, you must start with x1. So this is the tangent at point P. So the gradient of the tangent at point P is nothing but taking the differences in y and the differences in x. Consider this example. We have to estimate the gradient of the tangent to the curve y equal x minus 2 squared at a point 4 and 4. So we have this coordinate for 4, and we're supposed to estimate the gradient of the tangent to the curve. So estimate the gradient of the tangent. Again, look at what we have. The gradient of the tangent is at 4, 4, right? Look at 4, 4. From here, from 3, this is 1 point. So it moves from x-axis once, and then goes up to y-axis 4 times. So we can take 4, divide by 1, and simply get 4. So this will be one of those easiest way we can find or estimate the gradient of the tangent to the curve when illustrated graphically. So now let's look at some exercises and see how we are supposed to handle that. So let's look at the first exercise. We are supposed to plot the graph. So we are given the function y equal x squared plus x minus 2. Using a scale of 1 centimeter to 1 unit, plot the graph of this function y equal x squared plus x minus 2 for -3 less than equal to x less than equal to 3 as the range and the domain of the given function. What we have, so we have this function y equal x squared plus x minus 2. For us to plot the graph of this function with the range -3 less than equal to x less than equal to +3, we need to choose integer values of x from negative to +3 and then compute the corresponding y values. So if we have the function, so our x value in this case, we have -3, and then for -3 for x, we are going to have y, which is equal to x squared plus x minus 2. If we apply -3, it will be 3 squared, that is 9. So we have 9 minus 3. We just substitute -3 in the minus 2. So this will give you 9 minus 3 minus 2 will be +4. We can take -2. Then 2 squared is going to be 4 minus 2 minus 2. So this will give you 0. We can take -1. -1 squared is simply 1 minus 1 minus 2. 1 minus 1 minus 2 gives us -2. For 0, we can take 0 squared is 0 plus 0 minus 2. So also we get -2. So we can take +1. So it becomes 1 plus 1 minus 2. 1 plus 1 minus 2 is 0. We can take now 2. 2 squared is 4. So it is 4 plus 2 minus 2. 4 plus 2 minus 2 is 4. Then we can take 3. 3 squared is 9 plus 3 minus 2 gives you 10. So by doing that, we are able to find the coordinates. So we have 4, 0, negative 3, negative 2, negative 2. So we are going to have, for 4, it is coordinate negative 3, 4. Remember, we used negative 3 here. So the coordinate becomes, this is our coordinate. Negative 3, 4, negative 2, 0, negative 1, negative 2, we have 0, negative 2, we have 1, 0, we have 2, 4, we have 3, 10. So those are our coordinates. So we have negative 2 and 0. We have negative 1, negative 2. We have 0, negative 2. We have 1, 0. We have 2, 4. We have 3, 10. So we simply use this point, this coordinate, to sketch a smooth U shape, which is going to be a parabola through the point. Let's try to do that. So from here we can have the X and the Y axis. And take a white marker, and then we were told, using a scale of 1 centimeter, the highest value we have here is 10. So we can have this up to 10. Negative 10. So this is 1, 2, 3, 4, 5, 6, 7, 8. You can extend this. 9, 10. Then we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, we do the same on the y-axis. 1, 2, 3, 4, 5, 6, up to 10. Ensure you use your ruler to have accurate drawing. So we can extend this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is 10. So we have the coordinate negative 3, 4. These are negatives. So we have negative 3, 4, 1, 2, 3, 4. So negative 3, 4 is here. We have negative 2, 0. Negative 2, 0 is on the line. We have negative 1, negative 2. Negative 1, negative 2. So let's say this is negative 2 here. So negative 1, negative 2. We have 0, negative 2. 0 on the x-axis, negative 2 on the y-axis at this line. 0, negative 2. Then we have 1, 0. We have 1, 0 on the axis. We have 2, 4. So 2, 4 is here. 1, 2, 3, 4. 2, 4. Then we have 3, 10. 3 up to 10. Can use a different color here. So it is 3 up to 10. So from here now you simply join the line, a smooth curve, parabola. From this point, use your ruler to join this point. You will see that you will get a parabola opening upwards. So this is what is required for us to do in this particular question. First of all, you simply need to compute and find the point of intersections and substitute. Since we are given the range -3 less than equal to x less than equal to 3, use it to compute and use your ruler to make a clear diagram. Do not follow my drawing. This is a freehand, so you should be able to use your ruler to draw that. Look at B. Estimate the gradient of the tangent to the curve at the point 2, 4. So to find the exact gradient now, we need to differentiate. So let's do that. So we are supposed to differentiate. So we take dy over dx. Dy over dx in this case will be d dx. D dx, that is d dx will be the derivative of that function, and the function in this case is x squared plus x minus 2. This function that we have here, right? So for us to be able to differentiate these, you know the basic rules of differentiation. You bring the power down, subtract the power by 1. So what happens here, if we bring this power down, we are going to have 2x, and 2 minus 1 is simply 1. So we are going to have 2x. The derivative of x squared is 2x, and the derivative of x is 1. So it is plus 1. And when you differentiate a constant number, you will get 0. When you differentiate constant number, it is 0. So the derivative of this function in B is 2x plus 1. Now, we were told at point x, and we have those points. Just a minute. Let's look at those points that we were told. We are told estimate the gradient of at the point 2, 4. So it means so let's have that down. At x equal to, we simply substitute our dy dx in this case. We can solve this in the next page and clean that up. So at x equal to, remember what we have for the differentiation dy dx, we have got 2x plus 1. 2x plus 1 becomes 2 times 2 plus 1, right? So that becomes what? 2 times 2 is 4 plus 1, we get 5. So the gradient in this case is equal to 5. That's how you are able to compute that, because you are told to estimate the gradient of the tangent at the point. So once we differentiate, we simply use the x value in order for us to find that gradient. The gradient is equals to 5. And you know, in the normal equation that we have, the straight line, we know that equation of the gradient of the straight line is given by y is equals to mx plus c, right? Where m here represents the gradient and c represent the y-intercept, the gradient. And in our case, we are given 2. 2 represent the x value and 4 represent the y value. So you take 2 as the differentiation, the change in y in respect to x, which we got to be 2x plus 1. So once we put 2 times 2, 4 plus our gradient. Look at C. Estimate the gradient of the tangent to the curve at the points -2, -1. 1, because -1 is the x value, right? So if we substitute -1 from our differentiation, we got 2x plus 1. So that becomes 2 into -1 plus 1. 2 times -1 is -2 plus 1 gives you becomes -1. So the gradient is -1. Question: the grid shows the graph of y equal x cubed minus 3x plus 1 that we have seen here is showing that the graph of the function x cubed. So this is a cubic function. So we're supposed to estimate the gradient of the tangent to the curve at the point where x is equal to -1.5. -1.5. So look at the graph again and tell me what you can observe. Again, the function is given as x cubic minus 3x plus 1, right? If we walk through this to estimate the gradient of this tangent, we first need to differentiate. So if we differentiate here, we are going to have dy dx is equals to d dx of that function, and the function is given as x cubic minus 3x plus 1. Again, apply differentiation, bring the power down and subtract the power by 1. So when we differentiate x cubic, we are going to bring the power down, we get 3, and subtract 3 by 1, it becomes x squared. Now let's differentiate 3x. If you differentiate 3x, you simply get 3. So we will have 3. When you subtract the power by 1, it is simply 1, so nothing is left. And then when you differentiate a constant, you get 0. So the d dx of this function becomes 3x squared minus 3. Now we can substitute 1.5 in x. So we are going to have 3 into -1.5. Then we square this, minus 3. If you compute this, you will get 1.5 squared is 2.25 times 3 will give us 6.75 minus 3. So this becomes 3.75 as the gradient. 3.75. B, we write down the coordinate of the point on the curve where the gradient of the tangent is equal to 0. So it means we set the derivative to be equal to 0, right? If we set the derivative to be equal to 0, we will simply have our derivative is what is our derivative? We will have our derivative, which is 3x squared minus 3. So we have 3x squared minus 3 is equal to 0. So if this is equal to 0, what is x squared? X squared is equal to 1, such that x is equal to plus or minus 1, because it is x squared. Now we can find y. To find y, at x equal to 1, we are going to substitute y becomes 1 cubic minus 3 times 1 plus 1. This becomes 1 cubic is 1 minus 3 plus 1 gives you negative 1. And we do the same at y equal negative 1. We substitute negative 1 cubic minus 3 times negative 1 plus 1. So we are going to have negative 1 cubic is negative 1 plus negative 3 times negative 1 is positive 3 plus 1 gives you 3. So it is equal to 3. So the point we are looking for therefore becomes 1. So we can pick a black pen to have that. It becomes 1, negative 1, and then we have 1, negative 1, and 3. So these are the points required in this particular equation. And you can check this solution, this exercise 8.1 from your student book. The answers is always at the back of the note, the back of the textbook without the steps. So this is how we got that answer. Now let's continue with gradient of a tangent as a limit. When we look at gradient of a tangent at some limit, so we want to look at it in terms of a particular function. So we can consider the problem of finding the gradient of the tangent at point A on the curve equal fc in that tangent. It touches the curve at one point, this particular point, point A. So if B is another point on the curve fairly close to A, value for the gradient of the tangent at A, as we move B closer and closer, that is to say we have B1, B2, and we can even move up to B4. The approximate value for the gradient of the tangent at A gets more accurate. So we say that B, as B turns to A, you see this arrow here represents turns. As B approaches A, the gradient of chord AB approaches the gradient of the tangent at point A. So the arrow represents approaches, right? It is one of those mathematical notations that you must be able to know what they mean, because you know, as mathematicians we don't have a lot of time writing sentences. So this arrow represented approaches or tends to, and when I put an equal sign with inverted U, it represents implies. So this implies and this approaches. So as B approaches A, the gradient of the chord AB tends or approaches the gradient of the tangent at point A. Consider the graph of the function y equal x squared. So the point A has those coordinates x1 and x squared, where x and x squared can be any value. So the point B has also coordinate x plus h and x plus h squared. When we compute these two formula, the gradient of the functions of those two lines AB can be given as x plus h squared. So it can be given as x plus h squared minus x squared. Divide all this by x plus h minus x, which if you compute by expansion using the if you expand this is like you have x plus h times x plus h. So if we expand x plus h times x plus h, we are going to get x squared plus 2xh plus h squared minus now x. So if we have x squared plus 2xh plus h squared minus x squared, all this will be divided by what we have on the denominator, x plus h minus x. So we have x minus x. So in the denominator, we are left with h. So here we are going to factor out some h, and we were left with 2x plus h. Finally, we will see that as h gets smaller and smaller, b gets closer to a. So as h gets smaller and smaller, it means that p approaches a, or p turns to a. And the line AB gets closer to the tangent of A. So we say that h tends to 0, or we say that h approaches 0. We can actually find a gradient of at A as h approaches 0, or as h tends to 0. Or what you will do a bit in the advanced mathematics, we call it epsilon, because in this case we are seeing that h is approaching infinity, and when h approaches infinity, it becomes infinitely many. So there is no way you can actually define the rate of that number.